Hello, I'm going to present our work exploring smartphone keyboard interactions for experience sampling method-driven probe generation. My name is Surjya Ghosh and I'm currently working as a postdoctoral researcher at CWI Amsterdam. And this is a joint work with researchers from Indian Institute of Technology, Kharagpur and Microsoft. Smartphone keyboard interaction-based emotion detection has many applications, for example, in mental state tracking or adaptive interface design. But at the core of these value-added services, there is a supervised machine learning model for emotion inference. Now, to construct this model, we need emotion ground truth levels, which are typically collected as a long-term user study known as experience sampling method. But manual self-report collection is time-consuming and fatigue-inducing. So we always require intelligent probing strategies, which will probe the user at opportune moments so that there is less survey fatigue. So with this background, let us try to understand the research question. So if we pay close attention to smartphone keyboard typing, we find that there are two key facets. One is the timing, that is how fast you are typing, how much errors you are making. And at the same time, there is a rhythm in which you type. So both of which translate to the time domain characteristics and frequency domain characteristics. So we leverage, or we ask this question, can we leverage those two kind of characteristics to determine or design intelligent probing strategies, which will probe at the opportune moments. So let us try to understand the keyboard interaction-based probing scenario. In the right-hand side diagram, you see that there is a text entry session from T1 to T2, where the user is typing in WhatsApp. And once he completes typing, he is asked how was he feeling by sending an ESM probe. Now, while answering this probe, he can mention that whether the probing moment was opportune or not. And from the text entry sessions, we can extract several typing related features, not text related features, but typing related features like pressure and typing speed, etc. And then we can combine those labels with the typing based features to determine whether the probing is done at the opportune moment or not. So now, as we all know that standard Google keyboard does not provide this facility to track typing, we have developed our own keyboard, which is similar to Android keyboard. And it allows user to type in the same way. And we also collect the emotion self-reports where the user can answer whether the probing moment is opportune or not. He can mention just no response by selecting the no response button, and it indicates that the probing moment was inopportune. We have run a 3-week in the world study involving 22 participants, and we have collected close to 3,500 sessions, and out of which 83% was opportune and 17% were inopportune. Now, with this data, what we have done, we have represented every session as a set of ITDs. So a set of ITD indicates the time interval between two consecutive typing events. Now, after we represent every session as a set of ITD, we extract set of time domain characteristics like session length, session duration, etc. And we apply DFT or discrete Fourier transform to convert the ITDs into frequency domain. From there, we extracted 4 features, number of peaks and 3 peak amplitudes, peak amplitude 1, 2, and 3. And then we compare, is there any difference between between these time domain parameters and frequency domain parameters when compared for inopportune and opportune moments. And we see that for all the timing domain characteristics like session length, session duration, session speed, and error rate vary significantly. Similarly, the number of peaks and first peak amplitudes and second and third peak amplitude also vary significantly between opportune and inopportune moments. So leveraging those, we have developed a machine learning based model known as, actually we have developed multiple models. One is TD, which is based on only time domain parameters, FT, which is based on only frequency domain parameters, and then the combined, which combines both the time domain and frequency domain characteristics. And we evaluated this model. We obtained an average F score of 93%. And we have seen by running the explainability analysis that session length and peak amplitude 1 are the top 2 discriminating factor between inopportune and opportune moments. So in summary, we can say that a smartphone keyboard interaction pattern has both time domain and frequency domain characteristics, and those vary significantly between the opportune and inopportune probing moments. And combining those, we can develop a machine learning based model which will probe at the opportune moments and make sure that the survey fatigue is reduced. We have developed this model and we have obtained an average accuracy of average F score of 93%. So these are some of the references that we have used in our work. You can refer to our paper for more detailed discussions. And with this, I thank everyone. And if you have any questions, we can take those.